An airbag is a rapidly inflating cushion that helps to prevent auto crash injuries. When there is a sudden deceleration of the auto, a switch is thrown which triggers the start of a chemical reaction that produces a gas. The chemical reaction employed is the thermal decomposition of sodium azide, NaN3. Upon heating, sodium azide decomposes rapidly to form sodium metal and nitrogen gas. The reaction is exothermic and rapid once it has begun. In practice, an oxidant is added to react with the sodium to form sodium oxide. When the reaction is triggered by a sudden application of heat, the hot nitrogen gas formed by decomposition of the sodium azide expands into the airbag. Expansion occurs in only about 50 milliseconds. After the initial expansion, the hot nitrogen gas cools and the bag partially deflates, freeing the passenger. Notice that no new substance has been introduced into this closed system during reaction. The large volume difference between reactants and products is due to the fact that one of the products is a gas.
Okay, so we talked about the standard molar volume. 1 mole is equal to 22.4 liters of a gas at STP. So this allows us to put this into our Moletown Road, and this allows us to use our volume of gas as another thing that we can go between. Okay, so let's go ahead and look at this first example. Here we have our balanced chemical equation for the airbag reaction. It says a car airbag is designed to fill to a volume of 40 liters. If we assume STP, remember STP is standard temperature and pressure, so 0 degrees Celsius and 1 atmosphere. How many grams of sodium azide are needed to produce the necessary amount of nitrogen gas? Okay, so really important. We have to be at STP in order to use our standard molar volume of 1 mole equals to 22.4 liters. If we are not at STP, we cannot do that, okay? So in this case we are, so we have a volume of 40.0 liters of N2 gas, okay? At STP. They want us to find how many grams of the sodium azide we need. So we want to go from liters of N2 to the grams of the sodium azide. So we're going to get out our Moletown roadmap and figure out how to get from liters of N2 to grams of sodium azide. Okay? So I'm starting over here at the gas volume grotto, and I want to get to grams of something else, okay? So, dropping things. All right, so the first step is to go from liters to moles. So I'm gonna go from liters of N2 to moles of N2. Drop that down because that's not what we want. Okay, now I'm in moles of A, so I can go from moles of A to moles of B. So this is where I'm going to switch to the compound I want. I'm going to go from moles of N2 to moles of the NaN3. Drop it down. Now I'm in moles of B. I can use my molar mass to go from moles of B to grams of B. Okay, moles over moles is our mole ratio, so let's circle it and label it. Okay, moles always gets a 1 except the mole ratio, so we're going to put a 1 here and a 1 here. Inside the mole ratio, remember we need the coefficients from the balanced equation. So for sodium azide, the coefficient is 2. So in next to moles, we're gonna put a 2. For N2, our coefficient is 3, so we're gonna bring that 3 down here. Grams always gets molar mass, so we're going to do 3 times the mass of nitrogen, which is 14.007, plus the mass of sodium, which is 22.990. That's going to give us a mass of 65.011 grams. Now, what do we do with the liters? The liters is always going to be equal to this 1 mole. So we have 22.4 in our equality for liters. All right? Liters of N2 cancel with liters of N2. Moles of N2 with moles of N2. Moles of NaN3 with moles of NaN3. Leaving us with grams of sodium azide, which is what they asked us for. So remember that to solve a problem like this, I know it's been a minute since we've done a Stoich. You're going to put parentheses around the top, and you're going to do this, times this, times this, times this. Close your parentheses. Divided by this, times this, times this, close your parentheses. So we have parentheses, 40.0 times 1 times 2 times 65.011. Close your parentheses. Hit divided by parentheses, 22.4 times 3 times 1. That gets us 77.39404762. Okay? Our initial number had 3 sig figs, so we're going to do 1, 2, 3. The number after that is 5 or more, so the 3 goes up to a 4. We dump the rest. So this is 77.4 grams of NaN3. All right? This is very much like stoichiometry we did last unit. We're just adding an extra equality. Let's try another one. Okay. So this one says, according to this balanced equation, how many liters of hydrogen gas are formed with 65.7 grams of nitrogen at STP? All right, so that's our given. They're asking us to find liters of hydrogen. All right, so the given goes top left with units. So I'm gonna put my 65.7 grams of N2 here. Drop it down. Okay, and now we're gonna grab that mole roadmap and we are gonna figure out how to get from grams of one thing to liters of another. So I'm starting at gram A and I'm going to the gas volume grotto on the other side. So the first step is go from grams of A to moles of A. So I'm gonna go from grams of N2 to moles of N2. Drop it down. Okay. I'm in moles of N2. My next step is to go from moles of N2, which is moles of A, to the new compound I want. So moles of A to moles of B. So we're going from moles of N2 to moles of H2. Drop it down. The last step is to go from moles of H2 to the gas volume in liters. So we can go from there to liters of H2. Now again, remember this has to be at STP. Okay? If it's not at STP, we cannot do this piece right here. All right? Moles over moles is our mole ratio. Let's circle it and label it. Moles always gets a 1 except the mole ratio. So these moles get a 1. My mole ratio gets the coefficients from the balanced equation. So hydrogen has a coefficient of 3. Nitrogen has a coefficient of 1. Grams always gets molar mass. So this is N2. So we want to do 14.007 times 2. It's going to get us 28.014. And then our liters, this is the moles to liters, so that's going to be our standard molar volume of 22.4. Okay? Grams of N2 are going to cancel with grams of N2, moles of N2 with moles of N2, moles of H2 with moles of H2, leaving me with liters of H2, which is what they asked us for. Fantastic. Okay. Remember, please, that we are going to go parentheses, this times this times this times this, close parentheses, divided by, open parentheses, this times this times this, close the parentheses. So parentheses, 65.7 times 1 times 3 times 22.4, close parentheses, divided by, open parentheses, 28.014 times 1, close parentheses, enter. That gets us a value of 157.60119994. We need to round to 3 sig figs, so we're doing 1, 2, 3. The number after that is 5 or more, so the 7 goes up to an 8. We dump the rest. This is 158 liters of H2. All right, these are nice, straightforward problems. I want us to do one that's a little bit more complicated. Let's try a really tough one. We're gonna do one where we use gas Stoich alongside the combined gas law. Okay? It says to balance the reaction below. The reaction takes place at STP using 5.67 grams of CH3 and excess O2. The resulting CO2 gas is cooled to negative 25 degrees Celsius at a pressure of 0.57 atmospheres. What volume would this gas now occupy? All right, so let's start with the very first instruction, which is to balance the reaction. We have 1 carbon, 2 hydrogens, 3 hydrogens. Ooh. So we're going to multiply this by 2 and this by 3. That's going to change my carbon to 2, so let's change that to 2 here. Now let's see what kind of mess our oxygen are in. We've got 4 plus 3, that's 7. That's no good. There's no way to make a 2 a 7. So we're going to go back and we're going to double everything. So the 2 turns into a 4, and a 4, and a 6, and then this should be a 7. So it should be 8 plus 6 is 14, 14 oxygens. All right, equation balanced. All right, now let's go ahead and look at, we need to go from grams of CH3 to liters of CO2, okay? Because the one value we don't have for the CO2, we know it's at STP, so that's an initial temperature and pressure. We don't have its initial volume. So by going from 5.67 grams of CH3 to liters of CO2, that will get us our initial volume, okay? So we're gonna put our given 5.67 grams of CH3, drop it down, and then let's grab our Moletown roadmap, and let's figure out how to get from grams of CH3 to liters of CO2. First step is to go from grams of A to moles of A. So we're gonna go from grams of CH3 to moles of CH3. Drop it down. The next step is to go across the mole ratio bridge from moles of A to moles of B. So we're going from moles of CH3 to moles of CO2. Drop it down. Okay. Our last step is to go from moles of CO2 to liters of CO2. And again, we can only do that because the reaction takes place at STP. All right. Moles over moles is our mole ratio. Let's circle it and label it. Moles always get to 1 except the mole ratio, so we're going to give a 1 to these moles out here. The mole ratio gets a coefficient from the balance equation. So the coefficient for CO2 is 4. The coefficient for CH3 is also 4. Okay? Grams always get smaller mass. So we're going to do 3 times 1.008 plus 12.011. That's going to get us 15.035 grams of CH3. And then this right here, moles to liters, is always going to be our standard molar volume, 22.4. Grams of CH3 cancels with grams of CH3. Moles of CH3 with moles of CH3, moles of CO2 with moles of CO2, leaving us with liters of CO2. Parentheses, 5.67 times 1 times 4 times 22.4. Close your parentheses. Divided by parentheses, 15.035 times 4 times 1. Close your parentheses and hit enter. This gives us 8.447489192. We need to round to 3 sig figs. 1, 2, 3. The number after that is 5 or more, so that 4 goes up to a 5. This is 8.45 liters of CO2. Now, this is where we need to go back and stop and think about our problem for a minute. The reaction takes place at STP, blah, 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 the resulting CO2 gas. So this is the volume, V1. So that's my initial volume of my gas. All right, so I'm going to make a list of all my variables that I have over here. So my V1, we just calculated, was 8.45 liters. Now remember, STP is actually a temperature and pressure value. This is an initial temperature of 0 degrees Celsius, which is 273 Kelvin. And then a pressure at STP is 1 atmosphere. Okay, the resulting CO2 gas, now we're changing it, we're cooling it down. Okay, so it's going to be cooled to a new temperature, T2, negative 25. So let's do our negative 25 plus 273. That's going to get us a Kelvin value of 248 kelvins. Okay? At a pressure of, so this is a new pressure value, P2, 0.57 atmospheres. What volume would this gas now occupy? So we are now looking for a new volume value. Okay, so looking at this massive list of variables that we have ones and twos, ones and twos, ones and twos, which means we need to pull out our combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. We have no N values, so we're going to get rid of the N. We are solving in this case for V2, our new volume. So when we're solving for that, the idea is to get it by itself. So I need the P2 and the T2 that are touching it to go to the other side. To do that, I'm going to switch their places. So P2 is on top. I'm going to put it on bottom on both sides. Cancels out. T2 is on the bottom. I'm going to put it on the top. Do that to both sides. Keep it equal. T2 cancels out. So my equation for V2 is T2 P1 V1 divided by P2 T1. Now we are able to substitute in all of our measurements. So the measurement for T2 was 248 Kelvin. The measurement for P1 is 1 atmosphere. We're going to go with, it's infinitely significant because it's exactly 1. So we're not going to worry about this one for sig figs. The volume, V1, we calculated was 8.45 liters. P2 was measured at 0.57 atmospheres. And then our T1 was 273 Kelvin. All right. Canceling units, atmospheres cancels with atmospheres. Kelvin with Kelvin, leaving us with liters. Stop and think. Does liters make sense for volume? It does. All right. When we put this in the calculator, remember we got to put parentheses around the top and the bottom. So we have 248 times 8.45 divided by 0.57 times 273. This gets us 13.4670084. Now this number we're not going to worry about for sig figs because it was a standard value, so we don't worry about it sig figs. This one is 3, 2, and 3. So our smallest number here is 2, so we're going to round our answer to 2 sig figs. The number after that is less than 5, so this is going to be 13 liters of CO2 gas.